past lecture, we have seen examples of elementary operations and see how to reduce a matrix in a row echelon form by applying row elementary operations. Here we will talk about the same procedure, but in the context of systems of linear equations. So we will see now how to apply the reduction to row echelon form of these matrices in order to investigate the solutions of a system of linear equations. To start, we state the following proposition. So we start from a system of linear equations that we write ax equals to b, be any system of linear equations. Then C is a solution of this system, ax equals to b, if and only if C is a solution of another system, which is written as u times ax equals to ub. So basically we take this equality, we multiply on the left by the matrix u, where u is any invertible matrix. And the proposition says that the solutions of these two systems are exactly the same. So if and only if has two implications. So first we prove the following implication. So we assume that C is a solution of the system, and we prove that C is also a solution of the other system obtained by multiplying on the left both sides by the matrix, the invertible matrix U. So in this case, we don't actually use the invertibility of U. This is always true that this implication is always true, because if A times C equals to B, that is the definition of for C to be a solution of the system of linear equations, then if you multiply this equality by any matrix on the left, M, the equality of course will still be true. Therefore, C is also a solution of this system of linear equations. In particular, in our case, when U is invertible, but we are not using the fact that U is invertible here. We will be using it in the next step, which is the opposite implication. So we assume that there is a solution, C is a solution of the system of linear equations U times A x equals to U times B. And in this case, we use invertibility of U. So we know that UA times C equals to UB. Now, if you multiply on the left both sides of the equation by U minus 1, the inverse of U, which it exists by assumption, we will be getting this equality exactly by the same statement that we used before in the previous implication. We just multiply this system of linear equation by a matrix on the left. In this case, this matrix is U minus 1. But by definition of U minus 1, we have that the left-hand side of the equation, U minus 1 times U is the identity matrix. And also on the right-hand side of the equation, we have U minus 1 times U, which is still the identity matrix. Therefore, we'll be getting an equality between identity matrix times AC, which is AC, equals identity matrix times B, which is B. As a corollary, we have that if T is any sequence of elementary row operations, actually C is a solution of AX equals to B if and only if C is a solution of this new system of linear equations, which is written as T of A, so the transform of the matrix A through the sequence of elementary operations, row operations T, and the known term, the constant term, is T of B. Okay. Now, T applied to any matrix M is exactly equal to T applied to identity matrix times M. We already remarked the following fact about elementary operations, that the action of elementary row operations on a matrix M can be obtained in the same way by multiplying M on the left by a certain matrix. What is the matrix that we multiply by? Is the identity matrix to which we apply the sequence of row operations T. If we apply T on the identity matrix, we'll be getting an invertible matrix. This can be easily shown. So T is a sequence, again, we have to use the T as a sequence of elementary row operations, so we will be getting an invertible matrix. Therefore, we can apply the previous proposition and conclude that TA is going to be equal to an invertible matrix T of identity times A. So it's going to be a particular case of U times A, where U is T of the identity. So if we call U T of the identity matrix, we can apply in a straightforward way the proposition that we stated before. Now let's apply the RC theorem that we stated in lecture 6.5 and see, using row elementary operations, if we can say something about the solutions of this system of linear equation AX equals to B. Let's proceed as follows. First, use row elementary operations on the block matrix A slash, let's say, B. That is the matrix that for which the first columns are the matrix A, and then the last column on the right is the vector B. If we use row elementary operation on the block matrix A slash B, we can reduce it, the old matrix, we can reduce it to in a row echelon form. The definition of row echelon form is in lecture 6.7. Then notice that if T is a sequence of elementary operations, the transformed of the matrix A slash B is going to be the block matrix of the following two blocks. On the left we have the block of the transformed matrix A, and on the right we have the transformed column vector B. The second step of the procedure is the following. We notice first that the rank of the matrix T of A equals the rank of the matrix is the same as the rank of the matrix of the block matrix T of A slash T of B, if and only if the rank of the matrix A equals the rank of the matrix AB. This is simply because that the rank of the matrix A is the same as the rank of the matrix T of A, and the rank of the matrix at the block matrix A slash B is the same of the rank of the matrix T of A slash B, but T of A slash B is precisely this matrix here, this block matrix. Okay, so there is this chain of equality which proves this equivalence. But the RC theorem tells you precisely that the system AX equals to B has a solution if and only if the rank of the matrix A equals the rank of the matrix A slash B. Therefore, we can use this equivalence to prove the existence, to check the existence of solutions in the initial system of linear equations AX equals to B by checking the quality of the rank of these two new matrices. Okay, the new matrices are T of A and the block matrix of T of A slash T of B. So hence we can establish whether AX equals to B has a solution or not by considering the echelon matrix T of AB instead of AB because of RC theorem. So what is the advantage of checking the quality of the ranks of the matrices T of A and block matrix T of A slash T of B instead of A and the block matrix A slash B? because the transform matrices T of A and T of A slash T of B are in row reduced echelon form. Therefore, they have plenty of zeros, and the rank of these matrices is absolutely obvious. We don't need to apply any algorithm. We can see it just by sight. It is totally evident. So the next question is, okay, so once I have established that the initial system AX equals to B has a solution, what do I do next? One may want to actually find these solutions. Okay, so we know now, suppose that now we know that the solutions exist, so these two ranks are the same. Then how do I find the solution? Of course, I can go back to the initial system of linear equation AX equals to B, and by substitution try to find the explicit solution of this system. But the key observation now is the following. We can actually replace the system AX equals to B with the new system T of AX equals to T of B. And by the previous corollary, that was a corollary of the proposition, we know that the solution of this system of linear equations are exactly the same as the solution of this system of linear equations. They are just the same as a set. Okay, so I don't need to go back from the beginning and find the solution of AX equals to B. I can just take the reduced matrices, go back to the associated system of linear equations, and continue from that. Okay, let's see an explicit example of this. For example, let's start from the following system: x minus y plus 2z equals to 2, minus x plus z equals to 0, and 2y minus z equals to 1. Now, the block matrix A slash B is formed by the matrix A of the coefficients of the unknowns of the system on the left. So we have 1, which is the coefficient of x, and then negative 1, which is the coefficient of y, and 2, which is the coefficient of z of the first equation, and so on for the next two rows. And then the last column on the right is just the constant terms 2, 0, 1 placed as last column. So this is the block matrix. Now, the procedure involves the reduction of this matrix through row elementary operation in order to make it in echelon form. Okay, so this is the procedure, just is the same as in the previous lecture, so we will be just doing it pretty quickly. We have this first operation, which involves replacing the second row by the row second row plus first row, so R2 plus R1, and we get this new matrix. So this new matrix is not in row echelon form yet, because we have a 0 here in the second row, but in the third row we just have a 1 0 on the left and not at least 2 zeros. So the instruction to be in echelon form is this coefficient 2 here in the third row. So therefore we use the negative 1 here coefficient in order to kill this number 2 through this operation, R3 plus 2R2. This new vector is going to replace the third row vector of the matrix. So the result is going to be this following matrix, which is now in row echelon form. As you can easily see, the number of zeros on the left is strictly increasing if we start from the first row up to the third row. Notice that here on the left, as we noticed before here, T of A slash B was the block matrix T of A slash T of B. So the first three rows on the left are precisely T of A, so the transform matrix of A. And the last column vector is the transform matrix of B. Step number 2 of the procedure involves noticing that we can check if the ranks of the matrix, of this block matrix, is the same as the rank of T of A, in order to find out whether the system of linear equation, the starting system of linear equation, has solutions or not. Now, rank of T of A equals to 3 because, well, this is a triangular matrix, and we have all elements along the diagonal that are non-zero. So the rank of this matrix is obviously 3, but the rank of the complete matrix, the one with the T of B as last column, cannot be greater than 3. Okay, therefore, the rank of the matrix T of A is going to be the same as the rank of the matrix of the complete matrix T of A slash T of B. Therefore, we have that the initial system of linear equations, which is this, has a unique solution by the RC theorem. Why unique? Because the dimension of the solution was given by the number of unknowns minus the rank of the matrix T of A. So in this case, T of A, the rank of the matrix T of A is 3, number of unknowns is 3, so 3 minus 3 is 0, therefore the dimension of the solution space is 0, so the solution is unique. The unique solution C of the initial system of linear equation is going to be the same solution of the new system of linear equation that we get using as a coefficient matrices T of A and a constant term T of B, exactly as we've noticed for the step number 3 of our procedure. We can start from this system, which we obtain by using this reduced matrix. Okay, and that spares us of few computations by substituting these, for example, this last equation, which is going to be z equals to 1 in the previous ones. So we can, this spares us of few computations in order to get the solution.